Greetings. Global warming. I'm sure you've heard enough about global warming. What the heck am I going to say that hasn't been said before? Well, I'm going to take a different approach. First of all, I'm not going to make any judgment about whether the world is getting warmer, though it appears to be. I'm not going to make any statements about humanity is responsible for it and we're going to reduce the effects by reducing quote-unquote greenhouse gas emissions. What I am going to discuss is the science behind it, starting from a couple of basic principles. How does the Earth get hot anyway? It gets hot from the sun. We can compute how hot it gets. In fact, we can compute how hot the planets get based on their distance from the sun and the amount of energy the sun puts out. Then we can talk about this thing called the greenhouse effect, analogous to why it gets hot inside a greenhouse. So what's going on there? What's going on at the molecular level? Let's talk about that. So after we're done with this, at least you'll understand, as well as I do, what is the basis of the warming of the Earth, this global warming, and how to quantify it. So based on that, let's just move ahead. I don't want to take a lot of time. I have a fair amount of material to cover. And again, I notice I have more subscribers. Maybe I'm getting a little too, like a wise guy here, but let me just take off my little hat. And let's get down to some business. Once again, thank you, and I look forward to your questions and comments. Let's get right into the description here. Now, before I dive into these charts, let me say a few things. First, I'm going to cover why is the Earth around 300 degrees Kelvin? How did it get that way? What is the main driver? And the main driver turns out to be the sun. Then I'm going to talk about the greenhouse effect. Talk about glass, then I'll talk about gases, and I'll talk about the intermolecular behavior that results in that. Then I'm going to wrap it up with generalizing to the planets and seeing what the greenhouse effect is on other planets. So as I said, the amount of sunlight hitting the Earth is a key factor. The reflectivity of the Earth is a key factor. Not all the light incident from the sun that's hitting the Earth is going to hit the Earth. A lot of it gets reflected. Some of it gets reflected off cloud tops. When there are active volcanoes on Earth, there are lots of clouds, lots of dust in the upper atmosphere. That increases the reflectivity of the Earth, and that drops the temperature. That's a well-known global effect. The other aspect we have to deal with is the amount of light that the Earth releases. So the Earth absorbs light, and then the Earth releases it. How does it release that sunlight? What form of energy is it? Well, it turns out it's infrared light, and that infrared light will be absorbed by the atmosphere, or it'll radiate back into space. We'll have to look at that. And finally, how does the atmosphere act? How does the atmosphere hold heat that enters it? We have to discuss that as well. The heat capacity of the atmosphere seems to be the key factor people are interested in. They claim carbon dioxide, methane increase the heat capacity of the atmosphere. We shall investigate that when we look at the intermolecular behavior and the spectra of these molecules. How we're going to model the Earth to begin with and the sun are as black body radiators. Well, you might ask, what the heck is a black body? The sun doesn't look very black to me. The Earth doesn't look very black to me. How can I model those as quote-unquote black bodies? But it turns out any mass will emit radiation. A black body itself is a theoretical construct, and it's really a model of a perfect absorber. And this absorber then re-emits light based on its temperature, whatever thermal temperature it's in. The Earth happens to be at a temperature
that corresponds to 300 degrees Kelvin. I've said that, and we're actually going to go and compute that in a bit, not quite at the moment. All objects emit light. You emit infrared light. So do I. That's about body temperature. A star emits, obviously, light in the visible region. Every object emits light. A hot coal is red. The sun, as you well know, is yellowish in color. Every body, no matter what, emits light. The light that's emitted depends on its temperature. How this will all fold in will become very clear. Let's take an example of a black body radiator. That's a human or an animal. Now we know that our eyes are tuned to see in the visible spectrum, but at night there could be things lurking out there. The military uses this all the time. Border Patrol uses this. They want to detect people. How would they do that in the middle of the night? Well, maybe you can detect the heat coming from a person. A black body will emit infrared radiation. Therefore, if you have an infrared sensor, and there are devices that do that, you can then create a thermal image of a person. So what appeared to be sheer blackness is now a visible image. That's one example of many of black body radiation. Let's look at the black body curve. This curve is one of the triumphs of physics. It was one of the things that led to the beginning of quantum theory. What's on the x-axis is the frequency of the spectra emitted by a black body, and the y-axis represents the intensity. 4 curves are plotted there, ranging from 300 degrees Kelvin Earth temperature up to about 7,000. Let's take a look at the sun. The sun is about 6,000 degrees Kelvin, and lo and behold, the peak of its black body spectra happens to overlap with the visible light spectrum. Our eyes are tuned to see the visible light. Just so happens, maybe it's more than a coincidence. We will show the Earth, given its position, given its reflectivity, has about an average temperature of 300 degrees Kelvin. Actually, it's a little bit lower if you didn't have gases that are helping to heat it up, and those are called the greenhouse gases. We'll talk about that. But one of the important things I'll leave you with here before we leave is the power spectrum of a black body goes as the temperature to the 4th power. So if you compare the sun to the Earth, you get 160,000.